Hi everyone, good morning. Good morning. Let me start sharing my screen. Just a second. Mhm. Okay. uh, all right. So, yes. So, in today's class, we will be discussing about few important topics. Before that, first, let us see what we have seen so far. We have seen about the basics of artificial neural network, architecture, right? And then what are the hyperparameters? Okay, and comparing it with linear regression, right? And then we have implemented gradient descent code, basic gradient descent code in Python, right? We have also seen other important uh, uh, aspects of ANN, artificial neural network, particularly in hyperparameters. And what gives this the non-linearity? Wait, let me put this here. Non-linearity. What is it that gives the non-linearity in ANN?
Activation function.
Yes, correct. Activation functions. It's a hyperparameter. And we have also learned how it is inspired by human brain. Okay. How it is inspired by human brain and how we can change the architecture in different ways and so on. It can be used for both supervised and unsupervised. So far, we are seeing all the models, examples of supervised learning. Okay, we will also see for unsupervised, right? So this one, and then particularly about optimization, optimizers. We have seen quite a few optimizers, gradient descent, stochastic gradient descent, mini batch gradient descent. What else, guys? Next is momentum,
Momentum.
and then
Adaptive.
momentum and
Adagrad.
Adaptive
okay,
gradient.
ADA grad, okay, and
RMS.
correct, and then finally Adam. Right, there are many other, for example, there is Adam NA, many other. So like this, so many will be there. The main ones is this. If you know one stochastic gradient descent, you can know the flavors of stochastic, sorry, if you know the gradient descent, you can know the flavors of gradient descent, like stochastic gradient descent, mini-batch gradient descent. Similarly, if you know Adam, you can know other flavors also, right? So that's not a big deal. Right. So anybody, if anyone asks you in interview, you should be able to answer all of these. Very important. This is like the brain. So I always used to tell in linear regression model, if it is there, the brain of linear regression is the gradient descent, right? The gradient descent algorithm, because this is the one which does the calculations and updates the weights and comes up with the best model, right? So similarly for ANN also, it is any optimization algorithm that you choose, right? Not only this, we have an activation functions also, we have options. We have sigmoid, we have tanh, right? ReLU, leaky ReLU, softmax, okay? And many others are there. We have to play with all of these, okay? Fine. So far, we have seen all of these, which is great. Now, actually, I want to just test one thing. Can you tell me what is the formula for softmax, guys? At least tell me when to use softmax.
Softmax is used when we have the multiple class
Mm.
in the output.
Mm. Okay. Okay. What is the formula for this
We'll take
softmax?
the probability of each, which has the highest probability, that will be the target one.
Yeah, tell me the formula.
E to the power of 5 and summation E to the
Yes, correct. That's it. What is this I? This I is nothing but every value in the vector that we get, right? So we know that here I will have input layer, here hidden layers, and here I will have, let's say, 5 this thing output in the 5 in the output layer. 5 neurons are there, right? So I will get, there will be some connections, obviously, right? With there will be one value here, one value here, one value here, one value here that I will get, right? So let's say this is 0.3, 10, 30, 0.72, like this. So we simply take e power 10 by e power all of this to know what is the probability of this one, right? That is exactly the formula. That's it. If you forget, just try to remember with respect to the intuition, right? Whatever value we get as an output here in the output layer, that will be taken to the power of e. Everything will be taken up power of e, and then now you just look at the probability, percentage of probability for each of this of the values. So you have to divide it by e power summation of this. That's it. Okay. This. All right. So I think this should be fine. Now let's see one thing. So whatever model we choose.
Please scroll up.
Yeah. Yes. Yes.
Scroll up.
What?
Just scroll up, please.
Huh. Hello. Is there any question you want to ask, or what is it?
No, just noting.
Okay, just try to take screenshot, or I'll share this. Okay. I want you to make all of this. You should be making all of this on your own. It's like notes that you have to make, right? On your own. You would be making notes in a different way, right? I am making it in this structured way. You can make it in a different way based on your understanding. Okay. Now let's come back, guys. See, whatever model you choose, in machine learning, deep learning, whatever it is, there can be majorly two problems with it. What are those two problems that are mostly possible?
Source of dimensionality.
Overfitting.
Missing the global minima.
Overfitting, underfitting.
Yes, correct. Overfitting, underfitting. Yeah, global minima in a way, that is also correct. If you don't reach to global minima, obviously you will not reach the best model. You may overfit or you may underfit. These two are the problems, right? And in case of linear regression, we have, you guys might have learned different ways to tackle overfit and also to tackle underfit, right? To tackle overfit, what are the different ways? We have L1 yeah,
L1,
L1, L2 regularization, correct. What else?
Elastic net also.
Elastic net also, okay. These are regularization techniques, okay. What else? Won't you also remove unimportant features that you will see?
Yeah, feature
Unimportant.
engineering and
Yeah, yeah.
feature elimination.
Yes, remove unimportant features. Maybe you will add more data. If the data is very small, any model will be overfit, right? If the data is small, any model will be overfit. So increase the data points if you have, reduce the features that are unimportant, right? Whatever it is, you will try to do all of this. If it is underfit, what will you do? Your model is underfit. So what will you do?
Add some complexity to the model.
Correct. Exactly. So increase the complexity of the model. That means, in simple terms, what we can say is add some polynomial terms. Right? Add polynomial terms instead of y equal to w0 plus w1 x1 plus w2 x2. Increase the complexity by having w0 plus w1 x1 square plus w2 x2 cube, something like this. Increase the complexity. So this is a straight line, but this is a curve. So this is a linear regression. This is a polynomial regression. This is one way you can do it to increase the complexity because it is underfit. Maybe your data is like this and you're putting a straight line here. It's not good enough. You need something like this, for example. So you will have this equation, but not this equation. Okay. But overfit means something like this, where your data is very like this and you have a curve like this. Or your data is vastly spread, but you have done overfit extremely like this. So both are not good. We rather get something like this. No, something like this.
Okay, for
And also
overfit,
here we can get something like, let's say, uh, something like this, let's say. Yeah, yes.
so for overfit, you have given one more time E. I have not understanding to read it. EKS and ET. What is it? Not understanding.
Elastic net,
Okay,
Vishal.
elastic. Okay.
Hmm.
It's elastic net. Okay.
Yes. Yeah, I mean, these are some of the ways. These are not the only ways. There are many other ways, right? These are just some of the ways. Okay. So in similar way, and also guys, please remember, these techniques, what I have explained is an example for linear regression that I've written here. When we deal with Bayesian tree, there will be other kind of techniques, right? For example, removing the depth, reducing the depth of the tree, and removing the
Post-pruning and pre-pruning.
yeah, and also removing some child nodes and so on. So many ways are there. That is for specific to Bayesian tree. This is specific to linear regression. What I example I've showed here, how to deal with overfit underfit. Okay, so like this, similarly, ANN is also a model, right? Or just consider deep learning model, anything. This is also a model. So won't this model also suffer from both of these issues in real life?
Yeah.
Yes, there is a possibility that this model also can suffer from overfit or underfit. Okay, first let us think about underfit. Okay, see, usually these models will not be underfit that much. It will not be. What is the reason? The reason is, look at the architecture of any ANN. There will be so many input neurons, and there will be many hidden layers, and there will be so many connections like this, right? Which means the architecture itself, model itself, is a complex model. It is not a simple model like linear regression. Linear regression can be underfit, sure. But a complex model like this cannot be underfit. And on top of it, if I add a sigmoid function here and tan h function here or ReLU function here, I'm adding an activation function also. Activation function, when I add, I am adding non-linearity, right? I am adding non-linearity. When I have non-linearity, when I had non-linearity like this, let's say, it will be a complex model, right? This non-linearity is a complex model compared to linear model. Linear model is a simple model. This curve, non-linear, is a complex model. And a complex model will be mostly overfit on the trained data. Mostly. But it'll less likely be underfit. I'm not saying it'll never, it'll less likely. So usually there is less chances that a deep learning model will be underfit. Okay. But let us suppose it has become underfit. Okay, because data is huge and you have taken a very basic architecture of ANN. Just one hidden layer you have taken or two hidden layers you have taken, but the data is in terabytes, right? Data is in terabytes. And you have taken a deep learning model with just two hidden layers. Let us say this is underfit. Now, what are the different things you can do, right, to overcome this issue, remove the underfitting issue? What do you think?
Add hidden layers.
Okay, fantastic. Add hidden layers. Very good. And
Add activation functions.
yes, activation functions also you can. Because this will increase the non-linearity. Okay. Okay, very
Add
good.
number of neurons in the hidden layers.
Yeah, you can increase the neurons. Initially, you might have taken 128 only in first hidden layer and 64 in second hidden layer. Now maybe you will make it 256 and this also 256. Okay. Yes, all these are different ways to overcome the underfit issue. Very simple and straightforward, right? Very simple, straightforward. It's just basic common sense. Your architecture is this way. It is too simple. Let's make it complex. That's it. What are different ways? Whatever components are there in ANN, hidden layer, number of neurons, connections, activation functions, increase everything. That's it. Okay, fine. Now this one is okay. Now let us say model became overfit, and this is highly possible. Model can become overfit on my data set. Okay, it is highly possible. So data, imagine data is in GBs of data. And I have taken a deep learning model with 10 hidden layers, right, and activation functions. All of this I have taken, and this became overfit on this data set. Now, what is the thing that I can do to reduce the overfitting issue? Not reduce, completely eliminate.
Remove some connections.
Add dropouts.
Yeah,
Okay,
dropouts.
great. Good. How did you? So, I think some of you guys already know these concepts. Nice. Dropouts. Dropouts is nothing but removing connections, guys. Okay, what else? I will explain for those who didn't understand what is this removing connections. I will explain. First, let us think about all possibilities which we can tackle overfit. What are the things we can do?
Remove the neuron number of neurons, reduce.
Hmm, 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 hmm. You can reduce hidden layers. Correct. You can reduce neurons. That is also correct. Right. And then
Manikant,
Engine activation function.
Manikant,
yes.
will multicollinearity be an issue here in this deep learning model?
What is it? Can you repeat?
Will multicollinearity be an issue here in this deep learning model?
Multicollinearity, it will not be as impactful as let's say linear regression. But it will still be you can have it, no problem. But it should not be too much because it will lead to definitely it will lead to overfit.
Okay.
Right. Yeah. It will lead to overfit because already a deep learning model is prone to overfit. Right. On top of that, your data is having multicollinearity, means multiple features that are correlated. Then
Yeah,
it
in
will,
order to reduce the overfit, then we need to check for multicollinearity, and if
yeah,
there is any such thing, we can remove that.
you can remove that. Yes.
Which
But
is
mostly people work on model side only. And I hope you guys know this too. Deal with overfitting issue. We can make changes in the model. We can make changes in the data. Both the sides we can make changes. In the data, what we can do, we will remove the correlated features.
feature engineering.
Yes. You can keep it as a part of feature engineering. Right. And then you can increase more data set. Right. And many other things. In terms of model, what we will do, hyperparameter tuning. Right. And increase the complexity of the model. Oh, sorry. This is reduce the complexity of the model. Yeah. Similarly for underfit also. Right. Both the ways, in both the directions we can tackle. Right. So mostly in deep learning, we will work on this. In this also we can work because many multicollinearity might be there in real life, which we can remove that as a part of feature engineering task. Okay. Yes, now let us understand this dropout or removing connections. Okay, so I'll have this. Okay, just for example, we will take this. And this. Okay, so this way there will be multiple connections as you can see. Okay, so on you will have all these. Okay. Now, when I say dropout, first of all, overfit, this has become overfit, let us say. This is overfit. DL model on a certain data set. Okay. And there can be many weights here. So why will any model become overfit? Because it is too complex and there will be, and complexity will increase as we have so many connections, so many weights. So one way is to remove one particular, this one hidden layer, right? And just have direct connections from here to here. Directly will have connections, right? That is one way. You can remove the hidden layer. Another way is to reduce the neurons. Reduce the neurons. So I'll reduce these. Okay, and I will reduce these in hyperparameter tuning. That is all okay. That will definitely yield good result. But once we have created a model, and then from this model we are making changes right on top of this. That is what we can do is we can remove some connections. Let's say I will remove this connection, and I will remove this connection. Okay, and this connection like this I am removing. Okay, and those connections will be removed randomly. Randomly remove connections. Therefore, what happens? Number of parameters will be reduced. That is the weights will be reduced, right? Initially, I may have total, let's say, for all of the connections, there will be weights, right? W10, W20 like this. Assume there are 150 weights and I have removed 10 connections in randomly in between. Therefore, now I will have instead of 150, I'll have only 140 weights. So the number of parameters have reduced or weights have reduced. Therefore, it reduces the complexity. Structure is same. Architecture is same. Same number of hidden layers and input layer, output layer. Same number of neurons. Same number of neurons. In between, randomly, some connections were disconnected to reduce the complexity. But there is one catch here that we have to understand. Okay. So let's see this. So here to here, this connection, it is there. Okay, now, okay, let me write it as 10. I'll be just putting random values, guys. 10, 12, 13, 17. These are weights for suppose, let's say. And this is 4, 6, 7, 11, 18. Okay. Now what happened is I want to remove this, and I also want to remove this. Okay, that will be removed. As you can see, those are removed. Those are removed. But the information will be gone, isn't it? There has to be some information flowing from here to here. And from here to here, some information will have to flow through the connections with the weights associated and the values in the neurons, right? But if I remove this, the information, and remove this, and I remove this, the information will not go completely from here to here, right? Therefore, to make sure that the information will be passed, we can remove the connection, no problem. But still the information should be passed, which means accordingly when this is gone, right? Initially I had 1, 2, 3, and 4. 4 connections going to this neuron, right? But I have removed this connection. Now I have only 3 connections, and from other red color everywhere also it is coming. So let us say initially I have 4, and then yeah, for total 16 connections are here. Total 16 connections are here, and 3 connections I am removing. Therefore, I am left with only 13 connections to pass information from here to here. Therefore, to pass the same amount of information through 13 connections instead of 16 connections, these weights also will be adjusted. These weights also will be adjusted. That is, initially it was 12. Now, because that is disconnected, maybe it will become, let's say, 13.5. Right. And then initially it was, this is 12, this is 13, and this is 17. Now, let me write this. 13 will become 18. 17 will become 14.3. No, for example. And why did this become? Because this connection got lost, or we have removed it. And here in red, and you can see other one, 6, 4, 6, 7, 18, 11. 18, 11 I am removing. 4, 6, 7 is there. Yeah, you can put something like 2. 9, and then 11.3. Right? Those corrections, weights got changed. Therefore, whatever information will go from here to here will be still possible. It will still go, which means the relationship is still getting learnt appropriately even after removing the connections. Relationship still getting learnt appropriately, which means initially when I had, let's say 1000 parameters, after doing the dropout, it became, let's say, 950 parameters. Right, and all of those will be changed. Initially, there will be some values that these parameters will have. Now, the values will be changed. Okay, that is a model that is representing the pattern in the data using 1000 parameters. Now we're using only 950 parameters it should represent. So appropriately values will be changed. It's same like having, let's say, W0 plus W1x1 plus W2x2 plus W3x3. And then you decided to remove x3. So W0 plus W1x1 plus W2x2. So obviously this W's will not be same as this W's here, right? It will change because I want this to represent the pattern in my data set, right? Using just 2 particular features. Right, accordingly, weights will be adjusted. Similarly, here also the values have to be adjusted. But I'm not saying it will completely change a lot. It will change a little bit. Right, and not every connections need to change. Only some connections need to change. Right, not everything needs to change. Only few, or a few will not change. Okay. So instead of representing using 1000, you represent using 950. So you have reduced the complexity. You have reduced the complexity because of the dropout mechanism. Okay, dropout mechanism. So reduce the complexity, and since you have change the parameters. Now it is good fit. It will be good fit, better fit. Okay, this is the idea, guys. And one more thing, when we actually build the neural network model, we remember we will do dot add, right? Dot add, and you will keep adding layers. Sorry, neurons. You will add neurons, size or number, and then you will add activation function, and so on. And then you can, by the way, you will have to add dense here. I forgot dense. Dense represents what? Full connections, all connections. Right? And then I can add something called as dropout layer. Right? I will tell 0.2, which means drop 20% of the connections. Actually, this is one layer, this is one layer, and there are connections formed between these two layers because I added one dense layer, I added another dense layer. And in bit and then I also added a dropout layer, which means it will drop 20% of the connections. Here, suppose I have 100 and here I have 10 neurons. So total there will be 1000 connections. 1000 parameters. But I will drop 20% in random. Therefore, I will have only 800 connections. Right? This is something which we can try.
Mani, can I ask one question?
Yeah.
So can we go to the previous diagram of how where we are removing the node, that 1000 thing? Yeah. So if we are removing, say, we have 1000 parameters, just scroll down. So when we have removed, say, drop 50 parameters, it becomes 950 parameters. Now, if the weights are changed, right?
Yeah, weights will change.
The total amount of information going is same, right? Then how the impact is going to be seen, because if I have the amount of information is passed down, right? So the same overfit thing will be occurring. So I'm trying to understand here.
No, it is not like that. So look at this. So any kind of a model will have to learn the pattern present in the data set, right? So one model can be like this, right? Another, if you want to remove overfit, right? If you want to remove overfit, doesn't mean the solution is underfit like this, right? This is underfit where the model failed to understand the pattern in the data set, or a model failed to capture the information present in the data set, right? We have to have as much information as possible, but still not become overfit. Something like this is the correct model. So I'll draw this again. This is overfit. And this is underfit. Okay. So I want something like this. Okay, this is good fit. Right. So the idea is to not to reduce the information being passed. Information should be passed, but the model should be able to learn in a good manner, but not overfit. Right? Information should be passed, but obviously the information should not have any multicollinearity, or it should not have any other issues, unimportant features that will lead to overfitting issue, obviously. But consider data wise, there is no changes need to be done. But you have created a model that became overfit on the data like this. So obviously you have to reduce the complexity. This is nonlinear. Okay. Now this is little less nonlinear. This is better. This is linear, but this is not good because it is underfit. It is not covering. So doesn't mean we have to completely reduce the information being passed data. As much as should be passed, everything is important. All records, all columns are important to be learned by the data set. But it's the responsibility of the model to learn in a good manner, but not become overfit. Right. So from the model side, we are making the changes to reduce the weights. When we reduce the weights, we know complexity will reduce. Therefore, automatically overfit will reduce. Okay. Is that clear? And apart from this, you can also do in parallel other kinds of hyperparameter tuning to deal with the overfitting. This alone may not be enough. We also have to do L1, L2 regularization. Okay. All right. Is this clear, guys, to everyone? Any doubts, questions so far?
Clear.
Clear.
Okay, great, great. So we can discuss about the next concept called CNN model. Okay. CNN stands for Convolution Neural Network model. Okay. What is this convolution? It is basically an operation, right? It is like simply like a getting the scalar unit of two, instead of two vectors, you will get two matrices, in simple terms. That is what nothing but convolution operation. But we should understand that this CNN was completely inspired by human visual cortex, guys. This model architecture and approach, how this model actually learns, and this model has been heavily used on images data. Okay. This model architecture and approach of understanding the images data has been completely inspired by human visual cortex, how we actually somehow recognize some things from images, So it is believed there are two major components in a human visual cortex. One component would look at the smaller units, and the other component will combine the smaller units to make a bigger unit, right? It will combine the smaller units to make a bigger unit, and then therefore understand what it is. Mostly we'll be using the second unit, that is we'll be looking at a broader picture rather than smaller details. But yes, initial learning is done through looking at smaller details, and then through combining the details to form a bigger object, right? And then understanding what that is. Okay. Now, I am saying that CNN is something we will use on images data. Okay. You will use on images data. First, we have to understand CNN versus ANN. ANN, when I say, see, this is also artificial neural network only, but this is the type of artificial neural network. I will just write it in bracket. This is type of ANN, where there are not every input is taken into account in the input layer. In the artificial neural network, every input is taken account in the input layer. First of all, let us understand some problems with ANN, and then we will understand why people had to invent or come up with a particular model called CNN to deal particularly with images data. Okay. And by the way, very important to understand, CNN can be used on any data, guys. It can be used on any data, not just images data. Okay. But it was developed particularly keeping images in the mind, right? But you can use it anywhere, right? What is the only condition to apply to, to particularly use any model? The input, whatever we give, should be somehow converted into numerical or numbers, right? And then you, out of this, you will get the logic or relation, right? Can models understand text data directly, images data directly?
No.
No, right? We see, every model is internally simply a bunch of mathematical operations. Linear regression is what? Y equal to W0 plus W1 x1 plus W2 x2, right? Which means it's a mathematical operation. Neural networks also, you see, it's a combination of weight and weight multiplied with this input plus weight multiplied this input, all addition, multiplication, subtraction, sigmoid, tanh, all mathematical. Mathematics can be done on numbers only, not on text data. What do I mean by 2 into, let us say 2 into RAM? It doesn't make sense, right? 2 into 4 equal to 6 equal to 8. This makes sense. So models will work only if the internally uh, everything should be converted into numerical. Okay, so your initial input can be images, it can be videos, it can be text, it can be tabular data with some columns having string values. Okay, some columns having string values, whatever it is, convert into an input, right, where everything is represented in numbers. Then you can run any model. So if somebody says, hey, CNN is only on images data, how is that appropriate? Right, I can up. Nobody can stop me from applying CNN on text data and people to use it, because text I can convert to numbers, and numbers means CNN also has internally all mathematical calculations. So obviously I can use CNN, but it is designed keeping images in mind. So it is important to know why it was designed like this. What is the use of such a design to have? Okay, for that we need to understand ANN. When we use ANN on images data, what is the drawback? So let's see the first important one. So imagine you have images. Okay, like this you have 100 images. Okay, and every image is of size 1080 pixel you take. There are 1080 pixels overall. Okay, great. So the input layer will have how many neurons?
1080.
Correct. And I will have two hidden layers. Okay, and I'll have an output layer telling if it is which digit it is, 0 to 9. So 10 output layers. Here I will take 500. Okay, let me take small. Here I will take 50. Here I will take 100. Okay, so these connections will be there. So now tell me how many connections will be there between these two layers. This is input layer. This is hidden layer 1. Hidden layer 2.
1,08,000.
Yes, so 1,08,000 connections or weights will be formed, isn't it? Hmm? These many connections will be there, yes?
Yeah.
Why? Simply because there are 1,000 neurons in first layer, 100 neurons in. I'm taking only 100. I'm not even taking 500. Usually we have to take 500, 1,024, 512, 256 like this we have to take. I took only 100. Still we got 1 lakh connections. How long will it take? And 1 lakh connections means will it become overfit or not?
Obviously overfit.
Yes, too complex. This is only in this layer, guys, by the way. And you multiply this to this. So here, how many more I will have? Plus 50 lakh connections, right? And then 50 lakh here. 1 second. So here I have one. Oh, sorry. This is not 50 lakh. This will be 100 into 5,000. So 100 to 50, so 5,000. 5,000 weights. Okay, plus 500 weights. Okay, so total 1 lakh, over 1 lakh connections. This is one issue. Issue is many weights, therefore, can lead to overfit, and it is slow to be built. Second, doesn't capture the pattern in non-linear way. I mean, it's not, I mean, it doesn't, I don't mean that in terms of the model. Model is non-linear, but the capturing of the pattern is not in non-linear way. What I mean by that is, let's take one. Okay, okay. First of all, understand this. Here I have pixels, right? I have pixels. 1080 pixels are here. Okay. And this pixel information goes to this neuron. This pixel information goes to this neuron. Like this last pixel information goes to last neuron. Correct? So what does this pixel represent? It may have value called 30. This may have value called 45. Okay. And possible values are 0 from 255. Right. Imagine it represents only black and white. 0 is white, 255 is black. Somewhere in between is gray. Okay, that is how let us say for assume. 0 is white, but 255 is black. Between is gray. So this is 30, this is 45, like this values will go. Right. So what happens is this entire part is this particular first horizontal part of this image. And this horizontal part of this image is this particular neurons, like this. So model only learns representation or pattern in a horizontal manner. It is learning what could be here, what could be here, what could be here. But do you think patterns will be present only in horizontal manner? Not at all, right? Imagine I have a car. Okay, so this horizontal manner is good. So model will be able to capture that there is a particular edge in this particular horizontal part of this image. But model, can it capture this particular structure? Model cannot capture because it will be looking at this horizontal and then this horizontal and then this horizontal. So it will fail to capture any pattern other than straight horizontal line or straight vertical line. If you can also take like this as an input, no problem. Anything other than that, it will fail. It cannot capture these round things, right? That is one more drawback if you go with simple ANN structure. Okay, is this clear to everyone?
No, it's not clear to me, Manikant. Why is it like that? Because like while we are
Because
there
you're
doing,
passing in this way only, right? You see,
yeah,
when
yeah.
you pass information like this is how the information will be there, and the combined together, right? So why will this model capture if there is this particular round or this particular round pattern present?
My question is like,
Hmm.
why do we have to send it in this way? Anyways,
Hmm.
like all the input will be sent together at the same time only, right?
Hmm. It will be
So,
sent together in a particular order, in a particular
in a
order, in a
particular,
straight line, right? We were not
oh, is
sending
it
it
so?
randomly. Yes, yes.
No, we are not sending it randomly. That I
Hmm.
am able to understand.
Hmm.
But this input parameters will
Hmm.
be all sent together at the same time, right?
Hmm. That is correct. Yes.
So all these patterns will be there. Like we did the project, I mean like another program, right, for the
Hmm.
number prediction. In
Hmm.
that, like we have sent everything at the same time and we are able to
Hmm.
predict the number correctly, right? Why is it not happening here? Even there, it was a handwritten one. There were usually
Correct.
curves.
Correct.
Hmm.
Correct. That is good question. That is because that was on 0 to 9. It was rather very simple pattern to capture, right? Uh, Complex patterns like capturing car or scooter, railway or a person, particular person, that requires more complex, that has more complex patterns. This is a very simple pattern, right? The
Oh, I see.
possibilities are, yeah, possibilities are 0, 1, 2, 3, like this. Only these patterns are there. But I don't, and all of these, most of them are in linear only. So if you see 0, I can fit it in one way here, like this, 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 this. I am able to do it, right? In one
Hmm.
line. It's not something where I need a complex. Handwritten can become complex sometimes, I agree. It can become like this, let's say. But still, it is able to capture something in this straight line. At 5, let's say, somebody will write it like this, right? So this, like this, it will be captured. Many. 6 is there. I can make it like this. This should be equal to this in terms of uh, when I make it little linear. Okay. 7, 8. But I agree. Handwritten will be more non-complex like
Yeah,
this.
the
That
one
is
which
there.
we did was handwritten
Yes, it's a
only.
handwritten, but still it is simple compared to other patterns.
Okay. Hmm.
Okay,
Hmm.
right? And we are not checking for these kinds of patterns available. So let us it also discuss how a human brain actually functions. So we look at small patterns and then we combine to make sense to form a bigger pattern. Okay, so imagine one of your friend is there. Okay, he has very beautiful long hair. Sorry for my diagram. Okay, and suddenly he has got his head shaved due to some reason. Right, instantly you will, maybe you will not recognize him instantly, right? Because he always has very long hair and suddenly it's a big change, right? So you have some uh, smaller parts put together that will form, let's say, this part, and then you have beard, that part put together to form a bigger part, right? Where that is how we actually grasp things using our visual cortex. And one more example is, imagine a car. A car has two wheels. It has this kind of a body structure. It has headlamps. Okay, it has this window, whatever it is. You see, you observe all these. When you observe all these and you look at something new one like this, then you will tell, okay, this is actually a car. It's clearly a car because you have formed connections by looking at smaller patterns. Okay, and even this is a window like this, smaller patterns, headlamps, and then combined you form a bigger pattern called is a car. But the same wheel might be used for scooter also, or a bike also, a cycle also, whatever it is, like this. So, but here when you combine this parts with this part, you will know that this is actually a cycle, not car. Okay, that is the way. And even smaller, for example, there is a window. There is a window. Okay, like this. And window you started recognizing by understanding that there will be some edges like this. And when they are combined together to form a rectangle or a square or whatever it is, and they have some glass thing in between, then it is a window. Okay, but the same thing when it is big, same thing when it is big, and it has a wooden thing or whatever it is, then you know it's a door. But how did you identify it's a door? First of all, there has to be some edges like this, right? And other kinds of door also will be there where you have um, some structure like this. Okay, it can be there, but everything is you see and learn. You see smaller patterns and you and grasp the bigger one like this. Okay, with this kind of an knowledge, people got inspired and built a CNN model. CNN model. Okay, so CNN model is one thing where we will not be taking the entire pixels, guys. I mean, we will take the entire pixels, but not take the entire connections. Not take the entire connections. We will be finding for patterns. I will first let me give you the intuition of CNN. Right, I'll go to some image. Just a minute. So CNN, what it will do is it will, in the same way, it will try to identify smaller patterns first. It will identify that there is an edge here. There is an edge here. There is an edge here. There is some sort of edge here. When you combine, this is a circle or a wheel. This is headlamp. This together will be called as car. That is how CNN will identify. Okay. So there has to be a series of pattern recognition, right? When combined together, another pattern will be recognized. So this is a pattern recognized as wheel. This is a pattern recognized as headlamp. This is a pattern recognized as, let's say, some rectangle or a square or whatever it is. And then combined together, it is getting recognized as something called as car. And people might try to go further and then classify it as what type of car: sedan, SUV, or maybe which brand: Ferrari, Lamborghini, Benz, Tata, whatever it is, what kind of a car. It will further, we can do that also. Okay. This is the idea of CNN. Go structure by structure. And now to do this, people use these operation called convolution operation. So here I will add why is this? That's fine. Let it load meanwhile. So here, what would happen is there will be pixels in these images, right? All these are pixels, this pixel, like this, all these are pixels. Okay. Now a part of this pixel will be taken. You can take it like this, let's say. Okay, and that will be given to the neurons. And another part of the pixels will be taken. Okay, these will have some values, right? Here. Okay, and what will happen is this will be multiplied with something called as a convolution matrix. Let's say -1, 0, 1, 0, 1, 0, 1, 0, 1, something like this, a convolution matrix. Right? And here I have this. What does this particular neurons represent? This set of part of the images of the image, right? And then this one is represented by, let's say, this one. This one you will simply do convolution operation with this. Convolution operation with this matrix. What is convolution operation is simply you will get the dot and okay, let's see an example. It's like vector multiplication only, simply. There is some issue with my internet. Hello, can you hear me, guys?
Yeah, we can hear you.
Okay, great. So let's see some example 20, 10. Okay, so this both multiply plus this both 0 plus this both 10. Okay. Similarly, do this with this. Okay, so that is 0 plus 20 plus 0. Okay, and then do this with this. So that is 30 plus 0 plus 10. So now if you see here, I will have minus 20. Here I'll have 20, and here I'll have 40.
Mani, this 2010, 30, 2010 is RBG values.
Sorry?
This 30,
Yeah.
2010 are RBG values.
Yes, pixel values. Pixel values, RGB, black and white, whatever you want to consider. Okay, that's clear, right? Hello.
No,
Okay. Okay. 1 second. Let me write it down again.
It's
Yeah.
columns of the first matrix with
not
columns of the
getting Mani.
second matrix.
Yeah, see, you have a picture or a image.
Hmm.
You have pixels for it.
Hmm.
Then how we are converting that? Okay, we have image. Image is nothing but collection of pixels. Okay, from there, what next?
Yeah, I'm continuing it. I'm explaining it. Yeah. So, okay. So you can take this. I want to give a better example. Just have a look at this. This again, I'm just getting it from this one online source, so it will be accurate. So this is the filter, or you can call it as a convolution matrix that represents something. It may represent a edge or a horizontal line. Okay. Now this is nothing but as if you are searching if there is a horizontal line present in your image in a particular place. So we will do a convolution operation of this horizontal image representation in this matrix on top of the image. So I will take this and do the convolution operation on this, and then on this, and then on this, and so on. Right? It is just a way of searching where is my horizontal edge. So if you look, this will
From
be
where we got this
1.2 into
edge?
1. This edge is readily available. It's pre-computed and readily available. And this has been computed using different deep learning models. This will be just like weights. These are pre-computed. So many images have been taken before, and people have computed the uh, uh, convolution matrix or filter matrix that would represent a horizontal edge or a vertical edge. So this is nothing but weights in that particular model. But for us, it is a convolution matrix or a filter. These are weights in the deep learning model, which got trained on lot of images to figure out the edges. Right? In that place, those weights will be representing the edges in a way, in its own dimensionality space. But these are readily available. You can just Google or you will go to the library and you will get it. Right? You don't have to worry about it. These will be again learned. These convolution filter matrix will be again learned. We will see this. Okay. But imagine now you already have this. First, we need to understand the CNN concept. So you have this. Now what we will do is we will do this with this. And then this with this. And then this with this. Okay. So let's see this. It will be 1.2 into 1 plus 1.5 into 0 plus 2.1. It is 2.1 into 1. Like this you will have to do. plus 0 into 0 plus 1 into 1 plus 0, 1 into 0 plus 0 into 1 plus 0 into 0 plus 1 into 1. Finally, we'll end up getting 5.3. Okay, so I'll write it here, 5.3. So this and this, when applied convolution operation, the value is this. Okay, similarly this and this part of the image, where applied convolution operation, you would get another value, let us say 3.5, and here 5.1, like this you will get. So what happens is, simply I am just checking if there is an edge present in this part of the image, this part of the image, and so on. So if you come back here, I know this is my image. Okay, and by looking at it, I can tell here there is an edge. Here there is an edge. Here, is there an edge? There is nothing here. So when I take a convolution matrix or a filter matrix, which represents a particular horizontal edge, right, and I do convolution operation on this part of the image, it will somehow tell me the information that, hey, no, there is no horizontal line over here. But the horizontal line can be the horizontal. Hello guys, can you please mute yourself? It's a lot of disturbance. Yeah, the horizontal line can be here or here or here or here, it can be anywhere. So we have to search every part of the image. This, and we are taking overlap because we don't want to miss any chance of a horizontal line being present in this place or this place, right? So we will take some overlap in searching. We are searching if there is a horizontal line here, here, like this. We'll keep on searching. We'll search here initially by just doing a convolution operation with a filter, and then here with the same filter, and then here with the same filter, and so on. Initially here it'll tell me that no, it's not there, and suddenly here it will tell yes, there is a horizontal line. Here no, here no, here no. Here yes, there is a horizontal line. Here yes, there is a vertical line. So we have to search for vertical lines also, because in an image anything is possible. In an image I can have horizontal line, vertical line, circle, cube, triangle, whatever. Many things are possible, right? So here again, like this horizontal line, many things will be searched. After that, what will happen? After that, there should be next layer of filter. The first layer of filter is with respect to edges, horizontal edge, vertical edge, right? Maybe something like circles, small patterns. Then the next layer of filter should be what? Can you guess? What can be there? When you have multiple horizontal lines or vertical lines too, when you have multiple horizontal vertical lines, what patterns can you form?
Any other shapes?
Yeah, tell what shape it is. Tell me some shapes.
Okay, square, rectangle,
Yes, square, rectangle, triangle.
triangle.
These are all possible, right? And from
Mm.
this, what is possible? What else can I form?
Whether it is a vehicle or any other thing.
Yeah. Even there will be more little bit.
Subcategories.
Yes, and finally, there will be pattern to maybe to have a car, bike, right? Like this. Or it could be just classifying cat or a dog. A cat, dog has certain kind of eyes, nose, body type, right? Everything. Right, but to reach there, first let us identify smaller patterns, right? And then car, bike, or cat, dog, like that. This is the way CNN works intuitively. Okay. Every part of the image will be scanned. It's like, imagine you are searching in every place if there is a straight line, right? Imagine you have this one, what do you call, what is this called? Magnitude, glass search, right? Whatever it's called. So you're scanning through the
Magnifying glass.
dictionary. Magnifying glass, yeah. Magnifying glass. You're scanning to the dictionary to see a particular word. Line by line, you're seeing. Everywhere you're seeing. Right? Same way, imagine through different filters, you're seeing if it is there, it is there, it is there, it is there, it is there. And when you know, okay, these patterns are there in the first layer, this is just first layer, guys. In this example, I have taken this filter, which represents horizontal line. But in the first layer of filter, there will be other, first layer, there will be other filters also. -1, -1, 0, 1, 0, 1, 0, 1, 0. This could be vertical line. So in the first go, that is between input layer and hidden layer, let us say. It's not exactly like that, but similar to that. We will search for all smaller patterns, horizontal line, straight line, maybe this particular semicircle, right? And any shape, small shapes, whatever, we will search. Okay, and we will get to know it is here, 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 it is here. That information will be there. And then it will again be passed on to next layer, layer, where you will have this kind of something like where this represents L. One horizontal line, one straight line combined. Okay, you found it. And then you have this one you found. Okay, this is this one. Okay, so initially like the so I should not take this one. So we'll have this. You search for horizontal line, vertical line. Okay, and then you got some output. And then here you will search for horizontal line, vertical line. Now you will search for this and you will search for this. Turns out they are there. And then you will get some particular, when you do convolution operation, this and this, you will get some particular output like this. And then again, this you will apply again some convolution operation for this, where this would represent a square. This would represent a rectangle. Okay, and you will get some output out of this. Right? So are you able to follow? Initially, you had these many pixels. You search for this, and after convolution operation, the number of neurons reduced or the values reduced. Then you search for this, and you search for this pattern. Then you have these many, and you search for, when you know that this is there, what could be naturally present? It could be a square or it could be a rectangle, right? And anything, a cuboid, whatever it is, you just keep finding. Right, and then from this, what could happen? Next pattern that you will search is maybe a rectangle sitting square on top of a rectangle, something like this. Whatever, different patterns are possible, right? So that is how this happens. Okay, so this is, I gave example for black and white, gray, black and white. But what if you have color image? For a color image, you will have one set of values representing for blue, other for green, other for red. And then you will have three filters. One filter for red, blue, and green. So everything is same, just that you will have three particular in between. Three particular filters and three particular uh, neuron structure initially. And this operation is called convolution operation, guys, like star operation, like this. Convolution operation. Okay. So now first let me check. Okay, this is one filter, filter 1, filter 2. Okay, this is my image represented in terms of numbers, in terms of RGB, which is getting applied something called as a convolution operation on top of the filters. This filter is straight line, horizontal. This filter is vertical, right? Filter 1, filter 2. Then you would get an output. This when done convolution, this image will have convolution with this filter. You will have something values, and this also will have convolution. You will get something values, right? So these both will again undergo something, another operation, and you will get one more and one more. Right? These both put together, you can say. And then again on top of this, you can have one more convolution you can have here. You can have one more convolution. You can add as many convolutions filters as you want. You're searching, right? I can show you some images. Anyway, tomorrow I will go again, explain all of these and show some images. It will be very more easy to understand. But so far, with respect to concept wise, at least is this clear? What is the philosophy of CNN or the approach of CNN?
Yes, Manikant, one doubt here.
Yeah.
So initially, like you've said that convolution matrix acts like a weight, right? So
Yeah, that is continue.
Okay, so in one hidden layer, we'll be finding all the edges that are matching. In the next hidden layer, we are going to find the next shape, and in the next hidden layer, is it so?
Yes, it is. You should not call it as hidden layer because we are not having, this is not like a layers connecting among themselves, but you can take that as an analogy. You are right.
Okay.
Okay.
So finally, we'll get one output.
Yeah, exactly. Exactly.
Yeah, okay.
One quick question, right? So you said initially the drawback of using this make it ANN, right? Because the connection is too high, right? So if you compress that image, right? If it is, I mean, instead of 1080, I compress to 100 plus 100 pixels, right? Then we can use an ANN, right?
It will be okay. No problem. It should be okay. But usually, yeah.
I mean, anyhow, we have compressing here also. We are reducing the pixel, right? Using that weight right here.
Yeah, but one advantage is, see, I will tell you here we are searching and forming patterns which are like this, like this, like this. Right. We are searching for patterns like this. Is that happening using ANN? No, right? Because you see in ANN, where is the diagram? Yeah, here. The search is happening like this, like this, like this, like this. Yeah. In case of CNN, I am clearly searching this way. Oh, this way. Yes. It's not, it's again, after this, again, I will search like this. Right. So multiple options can be identified. This one, this one, this one, this one. And again, we are learning the next patterns also, deeper level patterns. We not only learn this, we learn this also. Right? So that kind of a learning is happening only in CNN, not in ANN. That particular shape level identification using the filters and then again identifying next shapes, next patterns is happening using only CNN. Searching for patterns available across the image. Okay. An ANN is mostly it will work only well on simple data, not a complex data. It will still work, but the complexity is very high. Time taking is very high, but you can compress the image and try it. But usually people will not do it because people usually want to enhance the quality. They will, deep learning models are used to convert black and white to color and all. They will take black and white and convert it into color. Right? And this is all done using CNN models. Right. Okay. Okay. All right. Fine. So that's all for today, guys. Tomorrow we will continue about the CNN. Also look at the Python code for CNN. And then we have RNN, GS, GRU. Day after tomorrow we will finish that. Okay. Fine. Okay. That's all for today, guys. Thank you. That's all for today. Have a nice day, everyone. Yeah.
Means we'll do this regularization like L1, L2.
Yeah, we can do that here.
Implement them.
Yes, we can do that.
Okay.
Okay. Okay, great. Thank you, guys. Thank you.